Hello, and welcome to this presentation on Applied Energy Symposium. My name is Kasper Størvaldsen. I'm a PhD at the Norwegian University of Science and Technology, NTNU, here in Norway. And today I will be presenting some of the work I am doing in my PhD. The topic today is methodology for achieving zero emission for a low energy building over a year using demand side flexibility strategically, where I will present a methodology using stochastic dynamic programming to capture the long-term effects of building flexibility when one is trying to achieve a zero emission goal over the course of a year. And this here is the outline of my presentation today. I just want to briefly mention that this presentation is about a planned paper that me and my co-authors are working on right now. We're expecting to have a paper finalized by the end of this year here, so keep in mind that the work you're seeing right now is considered a work in progress. So in terms of motivation behind this presentation here, one of the things that I want to highlight a little bit is that within the building sector, there has been done a lot of work to try and make the buildings a part of the solution to combat greenhouse gas emissions today, since the building sector also contribute currently on a sizable amount of greenhouse gas emissions. This has been done both in terms of how can we create more efficient buildings, but also how can we operate existing buildings more efficiently and cost effective so we reduce the emission they emit. In Norway, this is a great motivation behind one of the FMEs, which is the Centers for Environment Friendly Energy Research, called the Zero Emission Neighborhoods, short for FME-SEN, in which they focus on trying to reach zero life cycle greenhouse gas emissions for buildings and communities. So in this work here, they're trying to analyze how can we make the carbon footprint lower and how can we especially make it zero emission over the whole lifetime. So a lot of work has been done on this previously, as shown as an example here on the right side, where they have tried to define the different phases of a building's lifetime and where there are some emissions you can put in each category. And you can see that the most critical one in order to be able to create a zero emission neighborhood or community is the use phase here, where you need to have positive emissions savings during that phase. So there is a real need to have accurate decision making during the operational phase of these buildings and neighborhoods in order to make sure that you can accumulate positive emission savings over a lifetime so that it can cover the remaining emissions on the other phases here. So in order to make these short-term models, which is used to operate the buildings in more real time, accurate, there is a need to have some long-term signals that the short-term models can react on. And that is some of the work that I am trying to present in this presentation here, is a methodology where we try to create long-term signals that a short-term model could perhaps utilize to make more accurate decision making. And this is a methodology based on what is done in hydropower scheduling normally, because in hydropower scheduling, they divide the operational phase into different phases. One medium/long-term phase where they look into, for instance, a year. And through the stochastic dynamic programming, they try to calculate the benefit of utilizing water in the reservoir based on the time of the year and the reservoir level, so that it can be represented as a nonlinear future cost curve, which then can be implemented as input into a short-term model that then can react on these price signals. And that is also what I want to try and present in this work here for a building instead. So then I can go into the methodology that I'm proposing here. The methodology that I want to use to make this nonlinear future cost curve is based off stochastic dynamic programming, the same way that is used in hydropower scheduling. Because when we use SDP, we can break down longer problems into smaller subproblems. So if we want to schedule, for instance, over the course of a year, we can decompose this into, let's say, a weekly stages that can be analyzed without having to analyze the rest of the year. So we can decompose the problem into smaller subproblems. And when we do this, each stage will be considered decoupled, but we can connect them in some way by introducing a future cost curve based on a state variable we want to analyze that we can put as what is happening beyond the horizon you are analyzing right now. So let's put a short example of this or a specification on this. The state variable is seen as a series of initial values of the variable we want to analyze the long-term impact of. In hydropower scheduling, that is typically the reservoir level, where we want to see what the current reservoir level has an impact on in the future. So in this work where we want to look into more maybe what is the current CO2 inventory that we have accumulated so far, that can also be seen as a state variable that we want to analyze for. So in a model like this, we typically start at the end of the year on the last stage, let's say the last week, and we analyze how will the building we are analyzing perform for a number of discrete state variables that we initialize with. So what if we analyze how will the building perform if it has accumulated 0 kilogram CO2 up to now? What about plus 100, minus 100? What will be the cost-effective impact on all of these different states the accumulated CO2 inventory can have? That way, when you have done that for a predefined set of state variables, then you can create a nonlinear future cost curve as shown on the bottom right here, which then shows us, in this case here, the marginal cost of CO2 compensation for a specific week. And then it will, in this case here, show, okay, how much will it cost to have 1 additional kilogram of CO2 compensated for in the future versus how much would it cost to perform it right now, which option would be the cheapest one. Then the model would be able to have a future cost curve that showcases, okay, how can we make that work in the future? And then you can consider, is it worth doing it now, or should I wait until the next week, for instance? And when you have a curve like this calculated in the current stage, then you can move to the stage t-1 and have this future curve representing the performance into the future. And as you start going backwards and backwards and backwards, you will have a more accurate future cost curve that will be representing many possibilities of how you can compensate this CO2 compensation, let's say. So right here, I just wanted briefly to mention the building that I'm using in the SDP algorithm so we can get a sense of what is included within the SDP algorithm decision making. We here have a smart single family house, which has 2 flexible assets present. The space heating, where it can control the indoor temperature between some boundary that we have set, and also a stationary battery that can be charged and discharged whenever we want. We also have some non-flexible assets like electric specific demand and heat demand, also covered by electricity. And all of this is tried to be controlled optimally so that we can minimize the total electricity cost, which is based on the real-time pricing, the real-time hourly CO2 intensity in the grid, which then has an impact on the future cost and accumulated CO2 inventory, which is then represented as a nonlinear future cost based on the SDP algorithm we have shown. So to test the performance of this methodology here, we now introduce a case study surrounding a low-energy building located in the southern Norway, where we try to schedule this building optimally so that it can reach a zero-emission goal over the course of 1 year. This zero-emission goal here is defined as a ZEB-O ambition level, which, as shown on the figure on the bottom right, is a level where we only consider the electricity usage or energy usage during the use phase. In this case here, we only consider the electricity usage. So in order to be able to get a zero emission goal over the course of 1 year, we assume hourly CO2 intensity in the grid from imported or exported electricity. This is based on a tracing algorithm that was developed by Dr. John Claus in the paper referenced on the top right here, where he made a tracing algorithm to find the average CO2 intensity in each bidding zone in Europe based on historical data. And we have used that as input into this model here. We assume that the state variable in this situation here is the accumulated CO2 inventory. And we assume that there is some uncertainty in this model where there are 4 scenarios per week that impact the electricity specific demand, outdoor temperature, PV irradiation, and so on. And we also assume that there if there is a deficit of CO2 accumulated CO2 inventory at the end of the year, you will have to pay a penalty at the end of the year. And for this case study, we will assume two different penalty costs, one based on the CO2 quota from 2019 and one based on 20 times that amount, equal to €1 per kilo CO2. So in the results section here, we are showing two steps of the case study that we want to analyze here. In the first step, we want to analyze how the STP methodology creates future cost curves for CO2 compensation, which is shown in the heat map on the top right of this page. And what this heat map is showing us is basically what is the marginal cost for extra CO2 compensation based on what week we're at and what accumulated CO2 inventory level we're at, which for all of these small steps here gives a continuous now versus later comparison within the building scheduling. So to create this heat map, we have started at the end of the year on week 52 and calculated backwards for all of these discrete states to week 1, showing us then a heat map of the marginal cost for CO2 compensation. And the marginal cost depends heavily on what kind of CO2 level you're at. So for instance, if you're operating in the yellow area, you're operating in a level where you're not going to be able to reach zero emission at the end of it, and will have to pay the penalty cost equal to €1 per kilo CO2 at the end of the scheduling year. Whereas if you're operating in the green area, you have such a high value of CO2 level that you don't need to the future cost for CO2 compensation is close to zero because you will reach it almost no matter what, because you're already at a good set point. So what this curve here shows is how the future cost is affected by the cost of flexibility available in the future. And within this model here, if we were to use these curves in a simulation phase, the model would then compare to, okay, based on the CO2 level we are the CO2 inventory we're at right now, what is the marginal cost increase of increasing 1 more kilo CO2 in the future? And then you compare it to the current day and see, okay, how much does it cost for me to schedule this extra compensation now? And then you would compare which one is the cheapest option, and you would either do it now or you would wait until the future because there is an expected better opportunistic situation where you can utilize that flexibility in a cheaper manner. And you can see that based on how many days you go to the start at the beginning of the scheduling, the area between the green and yellow is quite bigger because there's many opportunities in the future to achieve this marginal CO2 compensation, which then shows that there is a high variety of starting values for CO2 compensation. You can start it at week 1, which should still technically mean you can reach zero emission at the end of the year. So what was also done, another step of this analysis, is that we did a short simulation phase of the performance of these CO2 marginal cost curves by utilizing a simulation phase where we solved each week sequentially based on the scenarios we have accumulated, different scenario threads. And for each of these scheduling weeks, we only represent the future cost curve as the horizon beyond this scheduling week. And the results of that is shown in the figure on the bottom here for the two cases, one based on the CO2 quota for 2019 and the other based on the CO2 quota for 2019 times 20. And the times 20 is the one shown in the figure on the top right. And you can see that if you're based on the CO2 quota in 2019, you're probably not going to achieve a CO2 a zero emission constraint at the end of the year, as shown by the orange curve in the middle one. The percentiles between them are 10 and 90%, but you can see that the expected value is expected to be minus 20 kilograms CO2 over the course of 1 year. But if you go for the high case with a 20 times penalty cost at the end of the year, the model manages to achieve a zero emission at the end of the year. As shown in the table in the middle, you can see that the ending CO2 inventory is expected to be 2.7 kilograms CO2. So based on the penalty cost at the end, you could achieve a zero emission, but for this 2019 case, it is not cost optimal to utilize expensive flexibility to achieve this. It's better to just pay the penalty cost at the end of the year. So this shows how the methodology based on the penalty cost can find a cost optimal way to achieve the zero emission goal, either by utilizing flexibility or by paying the penalty cost you have specified. So to conclude, in this presentation, we have presented a methodology using stochastic dynamic programming to represent the future impact of current decision making. This methodology analyzes the impact of the accumulated CO2 inventory to make a nonlinear future cost curve for a building trying to achieve zero emission over the course of a year. It shows the cost optimal decision making you should do so that you don't have to pay a penalty cost at the end of it if it is cost effective for you. And we have shown in a case study how the methodology could utilize the flexibility within the building to acquire zero emission over a year. And based on the penalty cost, it would either be best to pay the penalty cost or to utilize more expensive flexibility to get that target. At the end of this, I just want to say thank you for listening to this presentation, and I would especially want to thank both FMS Inaldi and FMS Sen for supporting my work and financing my PhD. And I really appreciate the support and help they are providing me within my PhD work with good colleagues that I can discuss with and propose silly ideas sometimes. Thank you very much.